you going to call when you have a problem? A chemist, because we have solutions. In today's lab, we're going to talk about solutions, and we're going to talk about how to make them. The first thing we have to do, however, is knew what a solution was. A solution is a homogeneous mixture that is homogeneous on a molecular or atom level. What I mean by that is homogeneous means it's uniform throughout. And when it's uniform throughout on a atomic level or a molecular level, that means if I was to do one of those little annoying circle drawings, what you'd see is every part of my solution is the exact same. That in any part of my solution, whether it's the top of the solution or the bottom of the solution, has one blue dot for every one red dot, right? One blue atom for every one red atom. It's mathematically uniform throughout on an atomic level, as in you've stirred this puppy really well. We see solutions all over the place in our everyday life. The classic example of a solution is salt water. Think about what you do when you make salt water. You take a spoonful of salt, you place it in some water, and you stir it around. I tell you this isn't rocket science, but it is. If you mix that salt in with your water really, really well and you take a drink of it, the first sip of water you take will be just as salty as the last sip of water because it's uniform throughout. We talk about solutions having two parts. We talk about them having a solute. Whoa, that's not supposed to happen. We talk about them having a solute. A solute is what is dissolved. In our salt water example, we're dissolving the salt in the water. So our salt would be our solute. What you dissolve something in is referred to as your solvent. In our example here, we're dissolving salt in water. So water is our solvent. All right, let's take a look at some classic notation here for writing solutions. If we want to look at our... Ooh, that gives me a good idea. Why don't you write down... Sports Center? Write down the word Sports Center. Sports Center. Write down the word Sports Center. Once you've written down the word Sports Center, I'll go back to writing sodium chloride. If I wanted to do chemical notation for a saltwater solution, I would write the symbol for salt, table salt, NaCl, and then I'd put parentheses, and then I'd put a cursive AQ. That AQ stands for aqueous, which means it's dissolved in water. Most of the time when you have a solution notation, what you'll do is you'll write the elemental name of the solute, or the chemical formula for the solute, and then you'll use the phase notation, parentheses with an abbreviation around it, to denote the solvent. Most of what we'll be doing this semester, nearly everything, unless something really weird happens, will have a phase of an aqueous solution. We're not going to be using solvents other than water really here. But when you get to organic chemistry, you might use hexane, in which case you'd have a parentheses HEX for hexane. So you can see other solvents there. But that's your notation. So whenever you see something like this, this is your solute, this is your solvent. And AQ means your solvent is water. All right, chemistry is easy, life is hard. Let's move on now that we have our definitions down. In addition to knowing what a solution is, it's important that we be able to express a solution's concentration mathematically. After all, that's why we as chemists love solutions. is because they're mathematically uniformed, meaning it's really easy to express their concentration. And there are a couple ways we do that. The first way we're going to express concentration is using percent mass volume. When you're reading a book and you come across something like the solution was 11% mass volume, sodium chloride aqueous, what they're telling you is that your solution is 11 grams of sodium chloride in every 100 milliliters of solution. Percent mass volume is always the mass of solute divided by the volume of solution times 100. Couple really important things to note about this formula. First and foremost, the bottom part here. It's volume of not solvent, but solution. Not the volume of the solvent, the volume of the solution. That is going to have a very, very important role in how we make solutions in the laboratory. So it's important that you realize that distinction. One of the reasons we stress that distinction is, matter of fact, let's talk about how we'd make a solution. Try this at home. It's really, really neat. Get a see-through measuring cup. I'm sure you've got a cup in the kitchen that's a see-through measuring cup of some nature. You know, it has a little handle there. Put some water in it. Put 100 milliliters of water in it. Or for your purposes at home, half a cup. Water and sugar loves to dissolve in water. Get some of that tablespoons of sugar and put a lot of sugar in there. You can actually get 80 grams of sugar to dissolve in 100 grams of water with no problem. But let's keep it a little bit more realistic since you don't want to be spending time applying heat or anything. And you dump 50 grams of sugar in your 100 grams of water. If you get that 50 grams of sugar into that 100 grams of water and then read the volume, you'll notice something really, really cool. You'll notice that the volume of water you have, or the volume of your solution, will actually be less than 100 milliliters. The sugar and water molecules love each other so tight, love each other so much that they pull each other closer together than the pure water molecules did to each other. I guess you could say water is the ultimate chemical bad boy when it comes to sugar. A lot of self-hatred going on. The water molecules don't want to associate with each other, but they really love some sugar, and therefore they want to get closer to the sugar than they did to each other. So you actually see the volume contract. Other times you'll dissolve a substance in a liquid, or such as water, and the volume of the solution will be greater than the volume of the water. Therefore, when we make solutions, we don't say, we don't base the solution off of the volume of the solute. We base it off the volume of solution. So whenever we make a solution in the lab, to make a solution, because of this changing size of solutions, let's make a note here. Because solutions have a volume different than the volume of solvent, when making a solution, add solute to a container, then dilute to the desired volume with solvent. Why don't you write down the word Cordelia? Write down the word Cordelia. I hope everybody's writing down the word Cordelia. All right, once you've done that, let's continue on. Cordelia, the good daughter from King Lear. So what do I mean by the fact that I say you add solute, then dilute with solvent? Let's go back to the example we started a couple slides ago. We want to make a solution that is 11% sodium chloride in water. And we want it mass... Let's see if I can't clean this up here for you a little bit. We want to make a solution that's 11% mass volume sodium chloride in water. And we want to make 100 milliliters of it. How would we go about that in lab? Well, remember from our previous slide that it's mass of solute over volume of solution. So if I want to make 100 milliliters of solution, that means I'm going to have 11 grams of sodium chloride. So the first thing I would do is I'd go to a scale and I'd balance and I'd measure out 11 grams of sodium chloride. There's my sodium chloride. All right, I'd get a piece of glassware known as a volumetric flask that's capable of very accurately measuring volumes of 100 milliliters. And we'll talk about volumetric flasks in great detail in a few seconds. It's made to hold 100 milliliters of solution. The first thing I would do is place my solute into that volumetric flask. So I'd place my sodium into my volumetric flask. Then I would dilute that sodium chloride with water. So I'd add my sodium chloride, and then I would fill up my flask with water until I had 100 milliliters of solution. How much water would I add? It would be greater or less than 100. I would add water until I had 100 milliliters of solution, until my volumetric flask read that I had 100 milliliters of solution, right? I'm not using a graduated cylinder or anything to measure exactly 100 milliliters of water, because I may need to add 110 milliliters of water to make that 100 milliliter solution. Or I may only need to add 90 milliliters of water to make that 100 milliliters of solution. You add enough water to make 100 milliliters of solution, whatever that volume of water is, right? So step one, measure your solute, then dilute to the desired volume. If you're making a solution that involves an acid, remember your safety rules: add acids to water or you'll be sorry. If you're wanting to make a solution that's 10% mass volume, hydrochloric acid, and water. What you would do is you'd follow the same procedure with one important safety exception. You'd add a little bit of water. Let's say we're wanting to make 100 milliliters of solution. You'd add some water at first. You might add, about 25 milliliters of water. Some water, but nowhere near that 100 milliliter mark, right? 25 milliliters, maybe even 50. And then slowly add your acid in. Then add your 10 grams of acid. Then dilute to 100 milliliters. So when you're working with an acid for safety, you add a little bit of water, then you measure your solute, and then you dilute. But when there's no safety issue, such as make salt water, you measure your solute and dilute to solution volume. You're still diluting to solution volume with your water here. However, you have to have a little bit of water in there to start off with for safety. Always think safety. Okay. A wild swing there. And let's work an example dealing with percent mass volume, a percent mass volume problem for us to solve. A solution is made by dissolving 13.621 grams of sodium chloride in 50 milliliters of water. What is the concentration in percent mass volume, assuming the addition of salt does not change the volume of the water? Percent mass volume is mass of solute. In this case, our 13.6219 grams of sodium chloride divided by the volume of our solution. Whoops. Times 100. I punch that into my calculator. And that gives me 27.2438% as the mathematical number. However, we have to take those fun-filled sig figs into account. I have 3 sig figs here, 6 sig figs there, so I should have 3 sig figs in my answer. So my answer winds up being 27.2%. Chemistry's easy, life is hard, yes? One quick note, I kind of brushed through the units. You're dividing mass and volume. Whenever you do this, you want to have units that are approximately the same. Remember, 1 gram of water has a mass of 1 milliliter of water at 4 degrees Celsius. Therefore, when we do percent mass volume, the mass is always in grams, and the volume is always in milliliters. Look at one more example. Before we look at this example, would you write down Philadelphia? Why don't you write down Philadelphia? I hope you're writing down Philadelphia. All right. How many grams of sugar do you need to make 250 milliliters of a 35% sugar water solution? In this scenario, they've given us a percent. Remember what Chemistry Cat says. If it's purring at you, you can use it as a unit conversion. In this case, because it's percent mass volume, you're being told that you have 35 parts of sugar, specifically grams of sugar, for every 100 milliliters of solution. So that percent is functioning as a unit conversion between grams of sugar and milliliters of solution. You're wanting to make 250 milliliters. Place milliliters of solution where they'll cancel out. Place grams where they'll be left. Multiply everything on top, divide through everything on the bottom. And that gives you 87.5 grams of sugar. So to make this solution, you'd measure 87 grams of sugar, then dilute to 250 milliliters with water. And on a multiple choice test, I will tell you right now, I will have more than one answer that will have that 87 grams. One of those choices would read, take 87.5 grams of sugar and place it in 250 milliliters of water. Choice E would be take 87.5 grams of sugar and dilute to 250 milliliters with water. This is how the answer is phrased, right? Because that volume of solution does not necessarily equal the volume of solvent. Right? So you never measure your volume of solvent. You measure your solute and dilute to the volume of the solution. I know I'm beating a dead horse here. All right. Before we end this video presentation, why don't you write down the word Yoda? Just because I'm looking at the Yoda on my desk. Write down the word Yoda. Once you've written down the word Yoda, we're done with this movie.